Okay, so let's continue recording from there. Let's go back to full screen. Okay, so we'll just briefly, you might wonder, why is Stan called Stan? It was actually named after a fellow by the name of Stanislaw Ulam. He was a co-inventor of Monte Carlo methods, going back to the Manhattan Project and such in the 40s. That's the name. So how do you get it? Well, most of the Stan interfaces you can download from the Stan website, which I just showed you. And RStan in particular is available from Paren, that you can download like you do any other R package from Paren. Documentation. Actually, I pointed out at one point the main Stan documentation. This is also a link to get it online. Also, and RStan, if you click on this link, you'll find a documentation for RStan. Of course, when you install RStan as an R package, you also get access to the help files in that process. So let's actually show you something about how to use it. So we're going to start out with a nice simple example. And in particular, it's going to be linear regression. We're just going to do a linear model using weakly informative prior distributions for our slope, intercept, and our residual standard deviation. Here we're going to write out our model using sort of statistical conventions here. So let's suppose we have a set of x's and y's here. Our data being, our dependent variable being the y's. So for each y here, a yi, that's going to be distributed normal with some mean yi hat and some standard deviation sigma. And that mean, that yi hat, is just going to be a straight line function of xi. And here, for prior distributions, I'm just going to use some fairly broad normals here for a and b. So I'll just center them at 0 and give them a fairly large standard deviation. In fact, that's probably major overkill. But for a simple model like this, it's not going to make a lot of difference. Same thing for the slope. And then for sigma, actually I'm being a little sloppy here. I said I'm using a Cauchy distribution with a location parameter of 0 and a dispersion parameter of 2. That's actually not quite right. We're actually going to use a half Cauchy. So we're only going to use the right half of the Cauchy distribution for this, and we'll see how we implement that. The data here, as I say here, I'm putting it as essentially as an R format. So for x, I've got a set of 10 values here as a vector, and similarly y, a set of 10 values that match up with those various x values. So you can think of them as pairs. So that's what we're going to implement. So let's start with our Stan model specification language for how we're going to write this out. A few general properties here. First, it's a very flexible model specification language. It's an imperative language, which means the statements are executed in the order in which they're written. Like probably most languages you're probably used to using, things like R and C and so on, would also be imperative languages. I mainly specify this because that's in contrast with another commonly used Bayesian modeling platform, Bugs, and its WinBugs, OpenBugs, and JAGs, because that's model specification language is a declarative language, which allows you to specify your statements in almost any order, but one consequence of that declarative structure is it makes it harder to do some types of calculations. Stan's got a full collection of computational control structures, things like if, then, else, blocks, for loops, while loops, and so on. It's got a very large collection of operators, built-in functions, and probability distributions. You can write your own functions in the Stan language as part of your models. It's got, as part of that collection of operators and functions and that, it's got a full, it's got full matrix algebra capabilities and such, which often simplify specifying models. Okay, now Stan programs consist of a sequence of program blocks. And there's actually a few more than the ones I list here, but the ones I'm listing here are the ones I would consider essential programming blocks. Pretty much any model that you're ever going to specify will have at least these 3 blocks. The first one is the data block, which is where you're going to be declaring data. In other words, these are data would be variables that remain fixed throughout the HMC sampling process. And then there's a parameters block, which is where you declare your model parameters. These are things which are function as random variables and which vary over the course of the sampling process. And finally, a model block, which is where the model calculations are happening. Notice each block begins with the name and then an open brace, and it closes with a closed brace. For each of these, here I illustrate one particular syntax for including comments, which is an R-like syntax where you can use a pound symbol. You can also use C-style comments here, where you can do a single line comment beginning with 2 forward slashes, or you can do block comments where you start with a slash asterisk and close it with an asterisk slash. So let's show you what some declarations look like in this setting. Now, first of all, one thing with Stan is you have to declare everything. So all variables have to be declared in here, and there's different variable types or data types. So there's the primitive data types would be real and integer. On the integer case, it's actually symbolized int, just like C. Then there are compound data types. There's arrays, where you indicate a size using a number inside of brackets. There are also vectors and row vectors and matrices. More on those later as we start using them. The variables may be bounded, and in some contexts you're actually required to specify the bounds. And in particular, if you're going to indicate a parameter, if you're going to give a parameter where the distribution, say a prior distribution has bounds, you have to also specify those bounds when you declare them. So let's look at this for our example here. So we're going to have a vector of 10 x values, and here and I say vector, but vector in the sort of loose sense, we're actually going to specify it as a real array, which is saying that, okay, the data type is real, the name is x, and it's going to have 10 elements. Same thing for y. In our parameters here, we're going to declare our intercept, our slope, and our standard deviation. They're all reals. In the case of our intercept and slope, they can be anywhere on the real line, but sigma has to be positive, at least non-negative. And notice here, here's the syntax for specifying bounds on a parameter. So in this case, I'm specifying it has a lower bound of 0 by saying lower equals 0. You can also specify an upper bound by saying upper equals whatever the number is. And if you have both, you separate them with a comma. Finally, in the model, we're going to be doing some calculations there. And that's illustrated here. So we're going to code the model and any additional declarations in the model block. The syntax looks similar to something like CR bugs. You use equals for assignment statements, and you use a tilde for sampling statements. And I just mentioned here, since different programs use different parameterizations for the normal distribution, they almost always use a mean for the first parameter, but Some use a standard deviation, some use a variance, or the bugs, for example, uses precision. Anyway, in this case, it's the normal parameters are mean and standard deviation. And our variables are it's variables that are declared in the model block cannot be monitored. By that I mean you can't save them for subsequent use after you've left the stand program. So basically a parameter declared in the model block remains in the model block. And I'm just going to specify, after I told you before that everything has to be declared, I told a little fib. The one exception to that statement is loop indices do not have to be declared. So let's illustrate some of these. So here you've got an example where I've done a declaration internal to the model block, which I'm going to use to hold an intermediate calculation. But again, that means I cannot collect the values of y mean outside the model block to do later inferences. Here I'm specifying my prior distributions. Here I'm specifying, A is normal, 0 with a standard deviation 100. Same thing for B. And here where I'm saying sigma is Cauchy. Now remember the statements I made about it being actually a half Cauchy? Well, the way that gets enforced is, recall up here when we declared sigma, I specified it had a lower bound of 0. And here I've assigned it to the prior to a distribution that normally would be over the entire real line. Basically, those two pieces of information act together to tell Stan that sigma is actually a Cauchy distribution truncated on the left at 0 by the bounds that I specified when I declared it. And then finally, I mentioned loops. So here's the syntax of a for loop. It looks just like in R, where I'm saying, say, for I in 1 to 10. And as I just mentioned at the end, you do not actually need to declare the I. It's understood that that whatever you specify for an index here will be an integer. And here you can see the calculations. Here I've got my calculation for my y mean for the ith value of y mean. It's just a plus b times xi. So again, looking all very similar to something like R. One exception throughout that you'll notice is every statement ends with a semicolon, and you'll get to learn that real quickly when you try to compile Stan programs that are missing semicolons. It'll let you know. Anyway, so everything ends with a semicolon. And finally, we have our final sampling statement here, which is really specifying the likelihood for our model parameters given the y in this. Let's see. Not much more to say on that. It's also possible to specify some additional code to generate predictions for model checking. And in particular, it's possible to use a sampling statement just like the one we did for our likelihood to generate samples for posterior predictive distributions. And so I'm doing that right here. Notice that this statement is just like my likelihood statement here. The key difference is y is a pre-specified set of parameter values, whereas y_pred is a parameter that's going to be simulated. So it plays a little bit different role. Later on, I'll show you another strategy that's actually more efficient for doing this kind of a posterior simulation. But for now, we can just I'll just show you this one just because it's the simpler one to write. Okay, so that's the model that we're going to work with. But a freestanding model doesn't do us a lot of good unless we've got something that lets us actually compile it and connect it to data and apply it to the data. And we're going to do that using RStan. So RStan is an R package that's available from CRAN sites. I just give an example of sort of the central CRAN site there. It contains several R functions for translating stand models to C++, then compiling the resulting C++ code, and then analyzing the data using the compiled stand model, and finally analyzing, summarizing, and plotting the resulting MCMC samples that are generated by stan. We're going to focus on only a few of those functions that are available in RStan, the main one being something called stan, which actually does, well, it does sort of in one go, does the first three of those functions. Excuse me. Okay, so what would an R script look like where we're going to use RStan? Well, here's an attempt to write what I've labeled here as minimal R code for our linear model example. So one of the first things we got to do is we got to pull in the RStan library itself, and we have to declare our data. Well, we have to structure our data so we can pass it to the appropriate RStan function, and the data format just takes the form of an R list. It's just a named list of scalars, vectors, matrices, or arrays. In our particular case, it's just two vectors, two R vectors listed here. You can see our X and our Y vector containing the X and Y values that we're going to fit a straight line to. The names and data types have to be consistent with the declarations in your stand model data block. Only numbers are allowed, no character strings, because there are no character string types in stan. So we've got that. Then we're going to specify some code for our initial estimates. As I comment here, initial estimates are not strictly required. Stan will generate some default initial estimates, and my comment in general is don't use them. I mean, don't use the defaults. I strongly recommend that you provide initial estimates yourself. I always sort of liken not providing initial estimates to sending somebody, off into the wilderness without a compass and hoping that they'll find their way to where, in this case, to where the posterior distribution is. And if you rely on something that knows nothing about the modeled system, it's likely to pick some initial estimates that are, off in another continent somewhere, and it makes it very difficult for the program to converge to a region of interest. So anyway, I strongly recommend that you provide your own initial estimates in some intelligent fashion. Now you can specify the initial estimates as a list or as a function that returns a list. My general preference is, as I mentioned here, is you can use a function that has a random number generation element in there that produces different initial estimates for each chain, and that's particularly desirable for convergence assessment because one of the best tests for convergence is whether or not different chains that begin at different points all converge to the same distribution. So the way I typically write it is I've got written here. You can see the for init here is being assigned a function that's returning a list, and notice how each of the elements here, A, B, and sigma, which there are three model parameters, are being generated in this case from either a normal or in the sigma case a log normal distribution, where I pick what I think are, I center them at a point which I think is a reasonable initial value, and then specify some variation around this so that so again each one of the chains will begin at a different starting point, that is hopefully not absurdly far away, but it still provides some test of convergence. And then finally the real engine here is right here, where I'm calling the stand function that you see here, which is one of the functions inside the rstand package, where in this particular case, I'm assuming that I've put the stand model that I just described in a file. In particular, it's a file called linear.1.stan, which is inside of a directory called the model directory out there. So this is specifying the path to that particular file containing the stand model. I pass in the data. I tell it, whoops, just hit a button I didn't want to hit. I tell it what parameters I actually want to get samples for. In this case, my intercept, slope, and my standard deviation. I'll tell it how many iterations. If I don't tell it anything else, it's going to assume that it will use the first half of that set of iterations for what the stand folks like to call warm-up. And during warm-up, you've got the process where hopefully you're converging to the posterior distribution. And second, it uses that phase also to tune the various parameters of the Hamiltonian Monte Carlo algorithm. And finally, I tell it, I pass in that function, which will generate my initial estimates. So that's where the main work is happening, is with that function. Okay, so let's go ahead and actually do the example. Okay, so let's get back to our in here. So again, this is the set of materials that I provided you. So the example we're going to look at is going to use this function here, linear1.stan. Let's actually go ahead and take a peek at what that looks like. Actually, let's go ahead and bring it up in, since I suspect most of you are probably going to be using RStudio, let's see if I can pull that up with RStudio. Come on, give me RStudio. Where is it? Okay. Oh, it's being a pain. Oh, here we go. There we go. RStudio right there. Okay, let's go ahead and make that the whole length there. Okay, so here's our model, and this is just a repeat of what you saw before. We've got our data block, our parameters block, and our model block in here. And I guess as long as we've now got a file window here, let's go ahead and use it. Let's go back up and down to the script block here, and let's open up what linear1.r, which is the file containing the corresponding R script. So that's the R script you just saw. But the only other thing I added in here is this libpath script, because we're going to be using the libraries or the packages which have been installed inside this lib directory here. So it'll be pointing to the right place. And the way I've written this is it's assuming that that the working directory is the script directory. So the first step here is go over in here, select, whoops, what am I doing? Sorry. We're in the script directory, so under more, the more menu, go down to where it says set as working directory. I'll click on that. Of course, that just generates a set working directory statement here. Alternatively, you could have typed that out directly yourself. Okay, so let's just go ahead and run this thing. I'll just go ahead and, whoops, select it and hit run, or if you prefer, you can hit source. That works too. Assuming everything was happy, make sure no error statements here. The red stuff here is actually all good stuff, so no problem there. It's still, sorry, it takes a while. With the simple model like this, the part that takes longest is actually compiling the C++ code that gets generated. Okay, so let's take a look at what it spit out. Stan is rstan, and Stan is somewhat verbose, so you'll get a bunch of stuff printed out, most of which is benign and less than useful information, but the stuff it's going through over here is all related to that compilation process. And then finally down here, it starts the sampling process. By default, if I don't tell it anything, it will use only one core on your machine, which is what it did here. It did each of the 4 chains in sequence. So it goes through and it did the first set. Notice how here it's stepping through, and by default it gives, let's see, as I recall, I think it gives a report every I'm trying to remember. It's not every 200 by default. I think it's every sort of 10th of whatever the total you specified. So in this case, 10th would be 200. So it's giving you a report every 200 iterations here as it goes through. Notice it's also reiterating while it's in Warmup versus when it's doing the post Warmup sampling in here. Before that, it gives you a little bit of information here that you could use to, as it says, adjust your expectations accordingly. It gives you some initial timing information. So now in this, it runs very fast for this example, but for a more complicated model or a very large data set, it could take quite a bit more. So sometimes this kind of information is useful so you can get some rough idea how long it will take overall. And when it gets done, it actually gives you a statement of how long it took for both the warm-up step, the sampling step, and the total. It goes through that for each one of the chains, and by default it does 4 chains. You have the choice, you can specify a different number of chains. And if it encounters any issues along the way, it tells you about them. So for example, this is telling you, what is it, the following numerical problems occurred the indicated number of times on chain 4. In this case, an exception thrown. In one case it says the scale parameter is 0 but must be greater than 0. That only happened once. That's both non-fatal and in a very small count. So as it sort of comments here, as it says, if the number in the count column is small, there's no need to ask about this message on Stan users. In other words, ignore it. Okay, so we've run it. Great, it ran. What do we do with it now? Well, there's a few different things that you can do that are already built in. There's built-in things like print and plot functions to deal with the object we created. Just a reminder, let's go back and show the function. So notice we did this calculation and returned the result to something we called fit. So let's take a look at fit. First thing you can do is simply type fit, and it'll pull up it'll use the default print method for the object. You can see it gives you some summaries of it. First, it reminds you, okay, what was the model? Well, the model was called linear 1. It did 4 chains, each with 2,000 iterations, 1,000 of which were warm-up, and it tells you whether or not you did any thinning. It tells you how many post-warm-up and so on. And total post-warm-up across all 4 chains, then it'll be 4,000. And then it gives you some statistics about various parameters. So we've got our intercept, our slope, our standard deviation, and something that here it calls LP underscore, which is the log probability. Basically, it's the log of the posterior, or actually maybe better to think of it as sort of being the log likelihood for this. That you could use that for some types of model diagnostics, but for now we'll ignore that. More key here is what we have is information about our intercept slope. standard deviation. So you notice we're estimating we have a posterior mean intercept of 5.73, 0.42 for slope, and 1.51 for sigma. The next column here, this SE mean, is a standard error of this mean, which is basically telling you how precisely does it think you've characterized the posterior mean. And here, so it's not telling you about the uncertainty of your parameter, it's telling you the uncertainty of your how you've characterized the posterior mean. And this is influenced by how many samples you do, as well as how much autocorrelation there is in the sampling. More on that in a minute. The posterior standard deviation is the thing which is telling you more about your uncertainty in the model parameter. It plays a role similar to the standard error of a typical parameter estimate. And then you get various quantiles here, or percentiles. So, for example, 50 percentile is just the posterior median. If you take the combination of the 2.5 percentile and the 97.5 percentile, that combination then is a 95% credible interval. So that provides an interval estimate for your parameters. So here you've got a 95% credible interval for your intercept that goes from 3.57 to 7.89, for example. One of the things we're always concerned about with these kinds of sampling methods is have we in fact converged by the time we got to the end of our warm-up period, and R hat is a diagnostic for that. You want that to be close to 1. Certainly you want it to be less than, say, around 1.05, and here you can see when it rounds off to this, it ended up at 1. I think it rounds off up to basically about the only thing we know if it says 1 is it's less than 1.01 when it reports it this way. If you want, you can get a more precise estimate out if you want. And finally, there's a thing here, it's called this N_F. That is something it's terming the effective sample size, which is essentially the equivalent number of independent samples. And here I have to remind you that with MCMC, we're dealing with autocorrelated samples because it is in fact a Markov chain. And almost by definition, there's some correlation from one sample to the next. The more autocorrelation there is, the lower this effective sample size will tend to be, and the less efficient the MCMC sampling is compared to independent sampling. So for example, in our case, the total number of post-warm-up samples is 4,000. So the best you could possibly do in terms of effective sample size would be 4,000. And in this case, what we have is, as you can see, somewhat different values, but they're roughly in the neighborhood of 1,500 for A, B, and sigma. So you can see they're somewhat smaller than sort of the optimal number of 4,000. Now these numbers here are not a problem. It's just that you want them to be big enough in order to support any kinds of inferences you're going to be making about that posterior, and to be confident that you've sampled enough to really characterize that posterior distribution. There are other things you can get out of this. Excuse me, let me take a look at something. Excuse the interruption here. Actually, does this thing let me pause? Yes, it does. Okay, let's get restarted. I took a little break from you. Short break for you, long break for me, but let's get back into it. Okay, there are a few other things that are built in, and I always forget some of them, so let me remind myself by looking at... oh, actually, did I get... looks like I removed it. Now, why did I do a silly thing like that? Okay, excuse. Okay, sorry, while I'm sort of, oh, I see what I just did, silly me. Let's go back to our hands-on session 1. Except I wanted to go the one before. There we go. That's what I was looking for. Sorry about that. Okay, we just did that example. Okay, stand trace. Okay, always forget the names of these things. Okay, if we do stand underscore trace, and then we have to specify fit as the argument for that. If I don't say anything further, and we do that, get that, you can see over on the left here, let's maybe make that a little wider so you can see it a little better here. Do that, and I guess I can zoom it up here so you can see even better. So here we're getting a set of so-called trace plots for our parameters. So we're looking at those are mighty tiny letters, but the left one is A, or our intercept, the middle one is B, is our slope, and then finally sigma over on the right. And you can see, and these are actually using different colors for the different chains. Remember, there's 4 chains. Of course, it does them in order. So the last one was probably this orange one, which is the easiest one to see. In fact, you can see there's a legend off to the side. And what you're looking for here is you want these things to be, as somebody other than me originally coined the term fuzzy caterpillars. And in particular, you want them to be horizontal fuzzy caterpillars in here. And that's more or less what we're looking at here. Not surprising, since our other diagnostics said we'd converge. So you're looking for them to be horizontal fuzzy caterpillars. You're looking for the 4 chains to all be describing approximately the same distribution. And that's certainly consistent with what we're seeing here for all 3 parameters. Now here we're only looking at the post-warm-up samples. It's going from 1,000 to 2,000. If you wanted to see the whole thing, including the warm-up, there's an argument. I think it's inc underscore warm-up. Yes, it is. That's one nice thing about RStudio, is it reminds me of those things. If I say true, I get a similar plot. But you'll see this sort of area with the gray background corresponds to the periods during the warm-up phase in here. And again, they had pretty much converged almost right from the beginning here. So no indication of convergence problems. Another plot I like is the pairs plot. Do that. That one always takes a little longer. Okay, we'll zoom that up. So this gives you a visual showing you sort of both the univariate. Oh, takes a moment to replot that. There we go. On the diagonal, you get the univariate marginal posterior distributions for the parameters you can see for A, B, and sigma. And we'll ignore LP and energy for the time being. You also get a picture of the bivariate marginals here. And in particular, you can sort of see how A and B are pretty correlated with each other, which is fairly typical of linear regression problems like this. Let's see, what else did I want to do here? Let me remind myself again from my slides. And that's the main ones here. Now, one of the things you don't get from this is I didn't do anything that really gives you a visualization of the model fit in this example. And we'll do that. We'll take this another step further. And in fact, that is mentioned on my slides here. Let's go ahead and bring this up full screen again. is I have another somewhat more complete stand model in our script for doing this that I call linear 2, and this is just pointing you to the pieces in there. And let's see, let me go ahead and show that to you. So same deal, let's go back to files, and I'm going to pull up linear2.r, and we'll go ahead and pull up the model, go to the model folder here too and pull that up. And the main thing that's different here is we're going to add in this ypred in here under our parameters and calculate that. Recall I showed you that before, so we're going to use that to do some posterior simulations. So let's go ahead and run that. That'll take a similar amount of time. So let's go ahead and just fire that right up. Okay, again, it takes a little bit of time to do the compilation. And then off we go. That reminds me of the things I do need to show you I haven't done yet. So let me show you a little bit about the R script I just did. Since before, as I said, I was giving you sort of a minimal R script. This is now an R script that's a template we're going to be using repeatedly in our subsequent examples here. So the key things in here is I'm going to go ahead and actually specify a model name in here, which will be our sort of the root name of both the R script and the model script. And we're also going to use that as a root name for other files that we're going to be saving along the way. I specify the paths to various places in here. So the script dir is our working directory that we're in. Project dir is the parent to that. Then I specify where we're going to save figures and tables, where the data is located. And actually in this case, I don't have a data file, so we'll use that later, but we're not really using it in this example. The model directory, which is where we keep the linear2.stand model in this case. This out dir is where we'll save some additional stuff. Tools dir is where I have some functions. So in fact, let's go ahead and show that to you. In the script directory, you'll see a subdirectory called tools. You click on that, you see a couple of files. I probably should have gotten rid of the stand tools old, but not important. The main one here is going to be the stand tools, which has a few different functions that I use in here. Probably the most common one, so we'll use, for instance, this MC history, which basically does organizes our trace plots for us. And then I've got this MC density, which again organizes a set of univariate density plots that we'll be looking at. So those are the main pieces that we're going to be using out of that. Okay, this is just basically something that if you haven't already loaded up all of your all the R packages and stuff, this will do that. Normally all it does is set the path to where the libraries are. Then we pull in the packages we're going to use. Our main one's going to be rstan. The stand folks have also developed a separate plotting package called Bayes plot that we'll be taking advantage of. And somewhere along the line, I've drank some of Hatley Wickham's Kool-Aid here, so I tend to do most of my data management using stuff out of tidyverse. Actually, I don't think we're going to use parallel in this example, but I do for many of the other examples. Okay, we'll move on. I set a seed, which again you don't need to do, but if you want to get repeatable results, that's a way to do it when we're dealing with things like this where we have a number of random number generation steps. Here I'm specifying the data as before, ditto for initial estimates. Again, that's just like before. Here I'm going to explicitly specify what parameters I want to generate history and density plots for, which in this case will just be my slope intercept and my standard deviation. But I'm also going to have some additional variables that I want to monitor and use for other things, in this case a posterior predictive check. And that's, in our case here, it's going to be ypred. So that I put under this other RVs, and I put them all together in a parameter called parameters. So this again is a template that we're going to use over and over again. I specify how many chains I want, how many post warm-up samples, and how many warm-up samples I want, whether or not I want to thin those samples. Here I'm just converting those to the parameter to the quantities which the stand function uses in there, and finally I make the call to stand. Here I've added a few things compared to what we had before. Data is the same as before. Pars is now inside that parameters thing. Again, that's telling it which parameters I want to save. Iter we've done before. What we didn't do before is I didn't explicitly specify how many warm up and whether or not I was doing any thinning, so I'm getting explicit here. The other thing I didn't do is I didn't explicitly specify how many chains. Now I'm doing that. In this case I happen to be using the same as the default, but if I wanted to specify another number I could. Something else I like to do is save that object that I called fit here to a file, so if I wanted to reuse it later, that's handy. Now in this example the fitting process is so fast that there's not a lot of benefit out of it, but if on the other hand, if you're doing something that requires hours to fit, but then afterwards you decided, gee, I really wanted to make I wanted to change the format of some plot or something, but I have to have all the MC samples to do it. Here, if you've saved this to a file, you can go ahead and uncomment this line here, which will load it back in without having to run the fit all over again. Then down here, this next chunk that I've labeled posterior distributions of parameters is some boilerplate that we're going to use in either identical or near identical format for our subsequent examples. I'm not going to go through all the elements of this, but what you find in here, first I declare a PDF graphics device, which is going to be saving all of our plots to PDF files. Here I'm specifying some formatting for these. The Bayes plot functions, which I'm going to be using, generate ggplot. So anything you know about using ggplot, you can apply to those to modify them. We'll make this one plot's going to create a set, recall that R-hat diagnostic for convergence. This will make a nice little plot where you can at a glance see all the R-hat values for the different parameters. Same thing for that number of effective samples. And then, well, there's something here which does an autocorrelation plot that I'll show you. We do MC history, we'll do the trace plots. Then we've got some density plots we'll take a look at, and the pairs plot. And then finally, it'll generate a summary table for our parameters. So that's sort of more or less boilerplate for our future use in addition to just this model. This other section that I've labeled posterior predictive distributions, it tends to be, you tend to have to customize that for whatever your model situation is. In this particular case, we're just going to do a simple y versus x plot showing both our observed values as well as our model predictions overlaid on them. So we'll take a look at that. Okay, so don't believe, did I run that one yet? Yes, I did run it. So let's go take a look at the results. And I'm going to, I find this file thing in RStudio a little slow, so we're going to go look at it from the Mac environment. So what we just generated has been saved most of the stuff we've done is saved in two places. Under deliv, which is short for deliverables, under figure, you'll see a directory called linear2, same thing under table. So if we go to the table one, this is just a CSV file. That's a little tiny, isn't it? Let me go ahead and open it up in something we can expand a little. Okay, that's not so bad. Okay, so this is that same sort of thing you get when you just type fit. You can see our A, B, and our sigma, which is what we said we wanted to save here. So you get your posterior mean, standard deviation, the various percentiles, number of effective sample size, the effective sample sizes here, which should be comparable to what we did when we did the linear 1 case, and the R hats. So this is more or less the same picture we saw before, but now saved to a file. And then finally our plots. We get a sequence of plots here. The first one just plots, well, it's overly simple here since we've only got 3 parameters, but it's plotting on the x-axis here is for our R hats. So it's just plotting them for the 3 different parameters in this case. It puts markers at sort of some key points like 1.05 and 1.1 and so on. In this case, they're all substantially less than 1.05, as you can see here. But anyway, so that just, when you deal with more complex models where you'd like to get more of an at-a-glance look at whether there's any parameters that are causing trouble in terms of convergence, you can get that very quickly rather than trying to go through the details of a table. This is the same thing, but now looking at the effective sample size divided by n. N is the total number, so here you can get some idea of how efficient the sampling is relative to independent sampling. This is an autocorrelation plot, which looks at correlations between different samples. So now, of course, for 0 corresponds to the correlation of a sample with itself, which of course always starts at 1. The second one here corresponds to the correlation between adjacent samples. In other words, samples only one step apart on the MCMC sequence. And you can see here, you know, for different parameters here. So and by the way, it also breaks them up by chain. So we've got chain 1, 2, 3, 4. But we'll look down here at 4. So here you can see you've got roughly 25% correlation between adjacent samples, and by the time when you get to 2 apart, it's down to what, you know, maybe 10% at most, and by the time you get to the third, to a separation of 3, you're almost down to 0. So there's not a lot of autocorrelation here, but there's certainly some. Next plot is our trace plot or our history plot. Again, you can see we've got some nice fuzzy caterpillars or horizontal fuzzy caterpillars, and all 4 chains overlay each other very nicely, which is a good thing. Here, this is our density plots where I'm plotting each chain separately for each of the parameters, so that gives you another diagnostic for whether or not the different chains seem to be describing the same distribution or not. In this case, they overlay each other pretty cleanly, so not too surprising for a simple problem like this. And then finally, this is just taking all 4 chains and putting them together to get a description of the univariate posterior distributions for each parameter. Again, this is our pairs plot. We've seen that before. And finally, we finally get a depiction of the fit, where you're looking at y versus x, where you've got the observed data as points here, and then a posterior median as a solid line, and a posterior, I think I did a 90%. In fact, we can double check that. If I go down here, You can see the calculations. I generate a 5th and a 95th percentile here, so that corresponds to a 90% credible interval about that. So you get a sense of how well we fit the data, as well as the uncertainty in our posterior predictions going forward. Okay, that was the story for our first hands-on example. Let's head back to our slides.